Imagine, you're a spy and you need to send top secret information to your headquarters. But you know that all your communication channels are tracked by enemies, therefore you need a common key that helps encode the information so that no one would understand it if the message gets intercepted. But how would it do that if you can't give the key to your headquarters by any safe ways? Let's simplify the problem down to the colored clay. Say you chose yellow as your private color and headquarters chose blue. Then you declare red as the public color. At this point, a message interceptor, say Dr. All-Seer, knows only your public color. Next, both you and the headquarters mix your private colors with the public one, having orange and purple, which you send to each other afterwards. Again, Dr. All-Seer catches them as well. Then you, the spy, add your own private color to the purple, and the headquarters adds its private color to orange. You both will end up with some strange colored mixture. Eventually, those mixtures will be the same, since you added the same colors, just in different order. And what about Dr. All-Seer? He just knows the public color and two mixtures, which gave him no clue about what were the initial colors, because what he wants is a specific information, the tone of your private colors. That's the trick. You use a function which is easy to compute, however, it's hard to reverse it. Such functions are called one-way functions. Such a one-way function for a computer may be raising numbers to different powers and finding the remainder after the division. Finding the remainder after the division is called mod function. For example, let's take 2, raise it to power 3 to get 8, and find its remainder after the division by 5. 8 mod 5 is 3. Now, let's take prime numbers, since for our enemies they are harder to work with. Note a cool fact: if we take 5 in different powers, its remainders when dividing by 23 would always be a different number. Even better, these numbers are distributed evenly, meaning that our enemies can just use probability to guess. Select your private number, say 11, and calculate 5 to the power of 11 mod 23, which is 22. The headquarters chose its private number, say 14, and calculates 5 to the power of 14 mod 23, which is 13. Afterwards, you exchange these numbers through a channel, knowing that it may be insecure, and raise received numbers to the power of your private number, and then again take a remainder after dividing by 23. Magically, you'll end up with the same remainders, since you did the same operations, but in different order. So, you'll get a secret key to encrypt the message of the sweetest candies in the city, and outsmart Dr. All-Seer, leaving him empty-handed. Of course, in real life you would use numbers which are enormously big, which makes hacking virtually unreal in the reasonable interval of time. It's a great algorithm for many reasons. Two parties don't need prior knowledge of each other, computations are low cost and easy to perform, and it's also pretty safe. Whether in the form of a padlock in your browser or a pop-up window in your iPad that asks to trust the computer when connected to it, the Diffie-Hellman algorithm lies at the basis of many security methods.